My name is Peter Newton from Vector GB, and I'd like to talk to you about challenges of electric and hybrid vehicle testing. So first of all, let's have a look at some of the components in an electric vehicle. So we've got the electric motor here. We may have one or two or more depending on the configuration of the vehicle. We've got a high voltage battery, and that battery is driving the electric motors through some power electronics. It's usually an inverter, so it's DC in and three-phase AC driving the motor. Out of the battery we might have a high voltage distributor box that may be feeding a compressor, or it might be a heater, or maybe a DC to DC converter for running 12, 24, 48 volt components in the vehicle. The battery needs to be charged, so there will be some unit that connects to an off-board charger that might provide three-phase power into the vehicle. We then have an onboard charger that will control the charging of the battery and the conversion to DC power for that charging process. Let's have a look at the inverter. It connects the high voltage battery to the electric motor. It converts DC current to three-phase AC and vice versa. So if we have regenerative braking, then the electric motor is driving three-phase into the inverter. The inverter then is converting that to DC power to charge the battery. It would use insulated gate bipolar transistors, IGBTs, that chops up the DC to convert it into the AC signal. Voltages could be up to 800 volts or more. Current ranges could be up to 1 kiloamp. And the transistors will be switching and sometimes up to frequencies of 200 kilohertz. We've got an example here, a little diagram, DC going in, AC sine wave current, AC current, and then the voltage is chopped to generate the power. So what are some of the challenges with testing electric and hybrid vehicles? Well, first of all, we've got very high voltages and high currents. So many vehicles are at 400 volt battery packs. Tesla is about 375, and the Porsche Taycan is 800 volts. So why have Porsche gone for 800 volts where everybody else has gone for 400? Well, one of the main reasons is you've only got a set of cables of a certain size, and if you double the voltage you can therefore halve the current for the same power throughput. And the current is a property that can cause heating in the cabling. So if you're reducing the current, then it means you're reducing the heating effect of that charging process. The flip side, of course, is that all your components need to be rated for that 800 volt battery, but we're reducing the heating impact. But because of those high voltages and currents, then safety is critical. The safety of the technicians, people in the garage, and the operator and owner of the vehicle as well. These currents can kill or seriously injure. They can cause internal burning, so we obviously don't want that. I had a hybrid car that I took in for a service, and I was told that the garage were going to quarantine my car. It actually took them 2 weeks to give it me back. They said there was a DTC reporting a fault with the coolant of the high voltage system. In the end, they said it was an erroneous DTC, and they'd reflashed the ECU and the problem had gone away. But yes, nobody was sure what the problem was and didn't want to really investigate without the right equipment. Because of turning DC into AC, we've got a lot of fast switching components, and these create fast transients on the power cables. So we need equipment that is fast enough to be able to record all of these transients so we can see what the system is doing. We also have components now that also generate and consume power. So the inverter is driving the e-motor, but the e-motor in braking is driving that power back into the inverter to charge the battery. The fast switching can also induce current flow in the shield cabling. And in the past, perhaps that wasn't something that needed to be concerned about. But now, because of the high power, we can generate a lot of current in those shield cables, and this can create aging. That's something else that needs testing. Performance of the vehicle is also required in specified voltage ranges, but over all the operating conditions. So in a hybrid vehicle, that'll be purely battery, purely ICE, and a combination of both. So we need to test for all of those situations. We may also have many additional sample points at a high potential. So in our battery pack, we want to measure the voltages between the battery packs, but also the temperature between them. So now we've got issues with packaging and wiring, and we need to do that on the test bench, but we also need to do that in the vehicle as well. So how do we fit all of those cables in? And then finally, measurement, synchronization and analysis. If we've got a lot of fast transients, then we need a lot of equipment to measure all of those transients, and we have a challenge of how do we synchronize all that data. And if we are measuring voltage and current into the inverter and out of the inverter, that could be 8 signals, that could be 8 mega samples per second. And then if we're doing additional online analysis, then there's a lot of data being generated and saved. So is our equipment up to the task? There's a lot of standards defining how we should test, UN standards, ISO standards, IEC standards. I'm not going to go into all of them, which is good, but they're covering rechargeable batteries, they're covering electrical properties of components and disturbance by conduction and coupling. We also have the WLTP, which is replacing the NEDC standard. It's now mandated since 2017, and this will look at the different drive cycles. So with a hybrid car, we start with a full battery, we do the drive cycle, and then as the battery becomes empty, we keep repeating the drive cycles. So we can look at consumption for battery power, ICE power, and a combination of both, and then we can give a consumption value. So we can record fuel consumption and CO2 more precisely now. We also record engine range, electrical range, total range, but we can also calculate all the powers and energies being used in that system as well. So let's have a look at a little bit of physics. So in a pure resistive load, we have the voltage and the current in phase, and all of the power is transferred to the load. So we can use this formula: power equals volts times current times the cosine of the phase difference. Phase 0 as a cosine is 1, so all the power is consumed by the resistive load. That's easy. When it comes to an inductive load, pure inductive load, the current and voltage are out of phase by 90 degrees. Therefore, we have positive and negative power flowing. And cosine 90 is 0, so the average power in the system is 0. The energy flowing to the load is equal to the energy flowing back to the source. Purely inductive, of course. But in your electric motor, there should be this phase value for the motor, and the smaller the phase, the greater the active power. So this is something that could be measured to see whether the phase calculation is correct. So we have active power, which is the power transferred to the motor to perform work. We see that formula there. We then have reactive power, power stored and released as a magnetic field or electrostatic field. That's a sign of the phase difference. We then have apparent power, which is the active and reactive powers as a root mean square calculation. And then for your electric motor, for instance, you have a power factor, which is the active power over the apparent power as a percentage. So these values can be calculated with the right equipment. So that's fine for a sinusoidal wave. With a non-sinusoidal wave, as we see the output from the phases of the inverter, then the power is volts times amps times the power factor. And you'll see here there's a little shift between the voltage and the current. But a three-phase motor requires both active and reactive power. Active power is converted into mechanical power, and reactive power is used to build the magnetic field. So if we just take a sample here, the voltage between the phases is a result of this switched operation of the inverter, and it's approximately rectangular. We then have an AC current coming out. It's a sine wave, but it's not pure, so we have this ripple on top, which could affect our circuitry. And then if we look at our DC, our voltage chopped up, then we see we've got these spikes. And these spikes and ripples can excite resonant circuits in our motor, inverter and cabling. So really they should be monitored and suppressed if necessary. So how do we measure this voltage and current? So we've got our battery, inverter, and e-motor. So we can break into the cable, put a shunt in here to record the current, break in and record the voltage. We could use a Hall effect sensor that clamps around the cable. We could use that to measure current. If you're a service provider or you're doing some back-to-back comparisons, you don't really want to break into the cable. So what you could do is you could replace the cable here with a module that will fit in between with the right connectors, and you replace the cable with this breakout assembly. You could do the same with the three phases of the electric motor as well. But the problem is that we can't look inside the e-motor and we can't look at the virtual ground in there without taking the motor apart. So here's three recordings. You can see the AC current of each phase and then the voltage difference between the different phases. And you'll notice that they are 120 degrees out of phase, each of them, which is the three phase. So one information can be calculated. Quite a lot. So we're measuring our power into the battery, from the battery into the inverter, and from the inverter into the e-motor. But here we've got a delta configuration. We can record the current going in, but we can't look at the current in the individual coils. So we need the current value to work out the power. We've got the voltage, but we haven't got the current. The alternative system is a star configuration. We can record the voltage, but it's the voltage over coil 1 and 2, and 2 and 3, and 3 and 1. So we can record the current going in, but we haven't got the voltage. So just by purely recording the voltage and current, we can't calculate everything directly from the motor. But with the right analysis software, it's possible to be able to work out those individual parameters to correctly calculate the power of each of the coils. But we can still calculate total power, active, reactive, lambda, and W. So if we can calculate the power of the electric motor, then we can calculate the power factor and we can compare that with the rated value. And therefore, with the right analysis software, we can test the symmetry of the coils, looking at whether there's equal power used by each of the coils. If we use a shaft encoder, then we can use that to compare the rotational speed of the motor with the frequency of drive of the motor. And we've got two types of motor, synchronous and asynchronous, used by different companies, and we can work out the symmetry and also the slip of those motors with the right analysis software. So here's power into the inverter, into the motor, and a shaft encoder. And we can work out the efficiency of that system. Shield currents, I mentioned those earlier. So as we have a switching voltage in our main core, this can cause currents in our shield cabling, and in the past that wasn't a problem. But as you can see from these two displays, this is over 100 amps, this one's 75 amps. If we're using our standard CAN modules, then we don't have sufficient sample rate to record this. So we need fast high voltage measurement methods needed. So 100 amps, as an average, this is quite a low current and it's a low millivolts potential. So it's not dangerous to operators. However, these high value spikes can cause heating in the shielding and therefore in components attached to the shielding. And this can create aging effects which may cause warranty issues further down the line. So this is something that now needs to be measured. We've got components like heaters. The heaters are heating the cabin but also heating the battery, because batteries don't work as well in low temperatures. So we've got heaters, but these components that are using high frequency switching can cause current and voltage ripples in circuits. And we've got some examples here. This is 12 volt system. This is a 280 volt system, and you can see there's a lot of ripple here. Overshoots in current can destroy fuses, connectors and cables. Overshoots are not wanted, so they should be measured, analysed and suppressed if necessary. Another case of spikes is if something happens with the load, for instance collisions with curbs, driving in off-road, driving over potholes where wheels spin, or slipping in mud and ice. So those changes in torque can cause stress and spikes in the electrical system. So therefore again they need to be recorded, measured and suppressed if necessary. So how can we help with all of this at Vector? Some of you are familiar with our VN family of hardware for measuring network traffic. We have our VX for looking inside the ECU to measure internal parameters. But we've partnered up with CSM, who make a number of modules for use in high voltage potential environments. So these can measure the current and voltage in our components and between components, and we can log those. Some of you will be familiar with the Canopy measurement and calibration software. We also have software called vMeasure Expert, which is purely a measurement tool, no calibration. And both of these, along with the offline tool vSignalizer, have e-mobility analyzer functionality. So we can log our voltages and our currents with the hardware, we can feed it into the e-mobility analyzer, and then we have these block sets for calculating parameters. So our three-phase input into our charger and our DC output can be fed in, and we can calculate various energies and powers of the charger. We've got a DC analysis module, feed that into the inverter as DC, and then calculate charge and energy and power and various parameters. And then we've got another one that for E-motor analysis. We have star and delta setup, three-phase in, and then we can calculate active, apparent, reactive power, frequencies. So it's a very powerful tool set for calculating on the fly or offline all of the parameters to analyze our test. So if you'd like to know more about these tools, then yes, please get in contact with us. Thank you very much.